Hey, good afternoon guys. This is Professor David De Los Reyes. Okay, my topic this afternoon will be a new topic. This is the third method of computing volume in integral calculus. We are done with the circular disk method. We are done with the hollow cylinder method. I give you examples on the on the circular disk, so many examples. On the hollow cylinder, so many examples also. So I will now try to discuss the so-called circular washer method of computing volume for regular and irregular figures in real life. Okay, let's proceed. My topic now is lesson number 76. It is on my channel under the topic Integral Calculus, under volume, and under method number 3 on how to compute volume, circular washer method with a close open parenthesis with hole. Circular washer, it's just like the what is called this the washer for bolts and nuts. Okay. Hold on guys, I will try to draw something. Washer is something like this. When I see with hole, there's a hole at the middle. Because under the method circular disk method, the hole is nothing. It's a solid block. So it's actually a disk. Okay, it's no hole inside. But for method number 3, there are times when we solve problems, okay, and what will come out will be a circular washer. That's why our main topic for this afternoon is circular washer method of computing volume. Okay, it is something like this. The washer and the bolts and nuts, the figure is something like this. There's a hole at the middle and it is circular. Okay, it got a certain thickness. It got an inner radius and an outer radius. Inner radius, outer radius. Okay, let's proceed. Sorry guys, I'll fix this one first. Okay. Let's proceed. Let's draw two graphs on the Cartesian coordinate system. So this will be the y-axis, x-axis. The first graph is this. The second graph is this. Okay, there is an intersection for the first graph and second graph. Okay. Then I draw a vertical slice. What's the significance of the area between the two curves? If the area under the two curves, okay, I will try to cross-hatch the area under the two curves. I will cross-hatch it, okay? I will remove this one. So the area represented by the red crosshatch is actually the area between the first curve and the second curve. And supposing they will ask you, if you try to rotate the area bounded by the first curve and the second curve with respect to the x-axis, okay, what will be the volume? Oh, that's the problem. Okay, so actually, if the first curve is actually, it's not within the x-axis, there should be a hole. Okay? So if we try to rotate the area bounded by the first curve and the second curve with respect to the x-axis, the question is, what will be the volume? The only way we could solve that one is by using integral calculus. The topics under solid mensuration, you cannot do it. no matter what. Okay? Because these are curves. It's not straight lines. For rectangular solid things, square solid things, or sphere solid things, okay, we could do it by using the general formula derived now. But for this one here, whether we like it or not, we could not solve the area bounded by the first and second curve. If we try to rotate it with respect to the x-axis, there should be no other formula that you will use for the computation of the volume of this. No matter what, you should use integral calculus. Set up your differential equation, then try to integrate. Okay? There's a note over here. Differential volume is formed when differential area is rotated. This is the differential area. Vertical slice. If we try, as seen from that view, this is the vertical slice. Okay? And if we try to rotate this one complete revolution with respect to the x-axis, the question is, what will be the volume? That's why it says here under the note, differential volume is formed when differential area is rotated with respect to the x-axis. For the meantime, it is with respect to the x-axis. Okay? If with respect to the y-axis, it will be a different figure, okay? We change our figure, okay? But for but the theory is still the same. The principle is still the same, okay? Let's try to bring out if this differential area is to be rotated with respect to the x-axis. The isometric configuration is this, okay? 30 degrees configuration, this is the x-axis, this is y-axis. And if we try to rotate the differential area, this will come out, okay? This is the center of the axis of rotation. This is the inner radius, represented by y lower. This is the outer radius, the bigger one, okay, represented by y higher. And the thickness of the differential, the vertical slice is actually the x. That's the view. It's a circular washer. That's why our topic for this afternoon is circular washer method. If the differential area is to be rotated with respect to the y-axis, the configuration will be something like this. Okay, this is the y-axis. This is the axis of rotation. This is the outer radius. This is the inner radius. As you can see it, there is a hole and the thickness is dy. Okay, I will now try to bring out the two sub-classifications or general equations on how to compute volume if it is rotated with respect to the x-axis, and secondly, with respect to the y-axis. Case number one, when rotated along the x-axis, the setup of the differential volume will be this. Differential volume will be pi times the quantity y higher minus y lower quantity square times x. There's a note over here. Y lower is not zero. Okay? Y higher is a function of x. Y lower is a g of x. Under circular washer, whether we like it or not, for it to be circular washer, y lower is not zero. So for the meantime, this is not an easy solution, okay? There is an equation for y lower. That's why I place it here, y lower is not equal to zero. The quantity y higher minus y lower is actually the radius of the washer, and the thickness is the x. And this should be the formula on how to set up the differential volume if it is rotated with respect to the x-axis. Okay? Case number two, when rotated along the y-axis, differential volume will be equal to, we will just change the variables, pi xr minus xl quantity square times dy. xl is not equal to 0, okay, because there is a hole. xr is a function of y, and xl is a g of y. G of y meaning it is not 0. And the radius is actually xr minus xl, and the thickness is dy. That is only the two cases under the so-called circular washer method. Case number one, case number two. So to compute for the volume under case number 1, try to integrate both sides. And you should know your upper and lower limit. That's your problem, guys. Even under case number 2, try to take the integral of both sides. Then try to place the lower limit and the upper limit. And so with this lower limit, upper limit. So actually what I am discussing this afternoon, guys, is the concept on how to set up the differential volume under circular washer method for case number 1 and for case number 2. It is a must that you should know this one. Like in the so-called differentiation, if you don't know how to differentiate a quotient, when you go to the solution of the problem, if you don't know the formula for taking the differential or differentiation of the quotient, you will be lost. Like here, under circular washer method, if you do not know how to set up your differential volume, you're gone. That's why in all my discussions, before I will give you problems, I will give you the concepts. Okay? So actually, this is the concept of the so-called circular washer method. Case number 1, and this is case number 2. Okay? It's always concept, the theory behind. Because it's hard to solve problem if you do not know the theory or concept on how to set up your differential equations. Okay? Okay, good afternoon, Los Angeles.